Hi, I'm Zor. Welcome to Unizor Education. We continue talking about conditional probabilities, and this lecture is about a very interesting theorem which was proved by a long time ago living individual. I can't even tell that he is a mathematician, Thomas Bayes, and he was Englishman. He was actually theologist, but he was really very good mathematician as well. I shouldn't really say he was not. And so this very simple theorem has his name. It's very simple. I will prove it to you in just almost like one line or two lines. But it has a very interesting practical applications. I do recommend to listen to this lecture from Unizor.com, because this is basically a part of the whole course of advanced mathematics for teenagers. So you can read the notes to this lecture. It's basically written as a textbook, and then listen to the lecture if there is anything which you might not really understand from the first reading. This is basically the suggested way of working with this website. Anyway, so let me go straight to this Bayes Theorem. Bayes, that's the name of the guy. Sometimes it's called formula, Bayes formula or Bayes theorem, doesn't really matter. So what I will do is I will actually present this theorem as a purely mathematical statement, which is very easy. And then we will talk about how to apply it in different cases. So here is the theorem. Let's consider you have certain sample space. Well, I can use a Greek letter omega, which sometimes is used for this, which contains certain elementary events. I don't know, E1, E2, etc., En, doesn't really matter. And if you have two different events, which is basically a combination of elementary events, right? Whatever the indices are, doesn't really matter. Then I have introduced the concept of conditional probability of event A under condition B, and we have agreed that this is a good expression for the probability of this conditional probability. Now, I really hate formulas which are not really supported by good understanding of what it is. So let me just deviate from my main theme of this particular lecture and again talk about this particular formula. This is an extremely simple formula, and all it does, it basically states that if you have certain number of elementary events, this is everything whatever is possible to occur. There are elementary events here, certain number. Let's talk about finite case, when you have a finite number of points inside of this area. And then you have certain event which encompasses only part of these elementary events. Then, geometrically speaking, the probability of this event is a ratio of number of points which are inside relative to the entire number of points in the area. Or if you're not talking about finite number of elementary events, and if you're not talking about elementary events which have equal chances, it's still exactly the same thing. Whatever number of points here, this area, let's use the geometric term area, divided by this area, represents the probability of this particular event. So it's nothing but really very plain geometric interpretation of the probability. Now, if for whatever reason you know that this is event A, now if you know that this event B actually has happened, which means all the probabilities are concentrating now from the entire space only into this subset, then obviously if you are looking for the probability of happening of the event A, all which is theoretically possible to happen are these elementary events which are inside the intersection, right? Because everything outside of B is not happening. We definitely know, this is our knowledge, before we even maybe conduct an experiment or we conducted some other experiment, that this event B is happening always, which means that the probability of all the points outside of this B is 0. There is no measure allocated. And all the measure is allocated to this particular subset B. Then obviously you have to divide only the intersection by the area of the entire B. Intersection divided by the area of B, to know what's the probability of occurrence of event A under condition that basically only events from the B actually can happen, right? So that's why I'm saying that this is a formula which you should not really remember as a formula. You should remember it as a picture. That would be that would be really the great way to understand it better. It's always the ratio of the areas. In this case, it's area of intersection divided by the whole area, because otherwise you cannot have any other event outside of B happening. So it's only the intersection between A and B which actually constitute events A under condition that B is happening, right? So that's my deviation, and that's how I, if you wish, derive the formula for conditional probability. But now let's talk about this way. If my conditional probability of A under condition B equals to this, the intersection of A and B, the probability divided by probability of B, then I can equally say that probability of B under condition A is B and A divided by period A, right? It's exactly the same formula, just A and B changed places. Now, obviously, A intersections B and B intersections A is exactly the same thing, because the set theory operation of intersection is commutative, right? So A intersect B is equal to B intersect A. So these probabilities are the same, which means what I can do is I can resolve it for this and substitute it into this. So the probability of A intersections B is probability of B times the conditional probability. So I have this formula equals. So instead of this, I will use this expressed as P B times PA of B divided by PA. So it's basically a one-liner derivation, right? And this is the Bayes formula. It combines two different conditional probabilities, B under condition A and A under condition B. Why is it so important? Well, to demonstrate how important it is, I will just go into a concrete problem, and in that problem I will try to demonstrate the importance of this. Okay, so let me go to a concrete example. Now, for this concrete example, I do need one very small formula, which is not really a theorem. It's just basically kind of an introduction into this problem which I'm going to do. Let's say, again, geometrically, this is your omega. This is your sample space. So all the elementary events are here. Let's call it E1, E2, En. And let's consider that they are of the same chances to occur. So every elementary probability is exactly the same and equals to 1 over n. If it's not that, it's exactly the same kind of logic. It's just simpler to assume it this way. Now let's consider that this entire sample space is subdivided into two different events, x and y. So let's say x has elementary events up to k, and y has elementary events from k plus 1 to n. Doesn't matter. The most important, they are not intersecting. They do not have anything in common. They divide basically into some unequal, generally speaking, parts, right? They divide the whole set of elementary events into two parts. And I also would like to say that their union is equal to entire space, entire sample space. Now, under these conditions, sometimes I will use different notation. Instead of intersection, I will use the multiplication sign, and instead of union, I will use the plus sign. Now, why is it justifiable? Well, basically it's just easier to write the books in this particular case and the text, but in general you will see that the probabilities are obviously supposed to be added. You see, the probability of x plus probability of y, it's the area of this and the area of this. It's supposed to be the probability of the entire space, right? Which is omega. So the union acts as a addition. Now the intersection is not really acting as multiplication, so don't assume that. But the addition is probably the most important, right? All right. So let's assume that my entire sample space is subdivided into these two mutually exclusive events. For instance, well, I flip the coin and there is either heads or tails, right? There are no others. So these are two events. Or if you roll the dice, it can be either odd or even, right? These are mutually exclusive events. Or it can be less than 2 or greater or equal than 2 on the dice. I mean, there are many different ways how any space, any sample space can be subdivided into two events. Now let's consider you have some event A, which also encompasses certain elementary events. Some of them belong to x, some of them belong to y, right? Now, obviously, it's obvious from the set theory I can always represent my A as a union of two different subset. A intersections with x, it's this one, and A intersection with y, it's this one. And obviously their union, or I like to really put plus sign here, because this is a union of non-intersecting parts. This is not intersecting with that, right? So similarly, the probability of A is equal to probability of A and x plus probability of A and y, right? Now let's remember our conditional probability formula. Let's do it again. That's the one which we just talked about, right? Okay. So, what does it mean in this particular case? Well, if B is actually x, I can replace it with So this probability of their intersection is probability of B, which is x in this case, times probability of A under condition B is x actually, so let's just use x plus. In this case, instead of B, that's y. So that's probability of y times probability of A under condition y. And this is still P of A. So you see, if my initial sample space is subdivided into x and y, I can always represent the probability of some event as a sum of probabilities which are calculated using this thing. So look at it this way. Well, event A can happen under some circumstances, right? So sometimes it happens if x is happening, right? And that's these things. And then obviously the probability of this piece, which is intersection of A and x, is the probability of happening of the x. That's what conditional probability is, times the conditional probability of A under condition x. Same thing this piece, that basically represents the probability of A under condition of y, right? So the area is equal to probability of y times conditional probability of A under condition of y. Why is it important to do this type of manipulation? Because sometimes we don't know the probability of A, but we do know conditional probability of A under certain conditions. And this is exactly the example which I would like to present to you. Let's consider I am in a business of selling the tennis balls. Okay? I have two suppliers. One supplier, oh, by the way, this is called a formula of total probability, right? So one supplier X manufactures white and green tennis balls, all right? So it manufactures white and green. And let's say it's 50-50. That's how it's produced. Now, the supplier Y manufactures also two kinds of tennis balls, two different colors. Yellow, 90% of the production goes to yellow. And green, 10%. Now, I'm buying from both suppliers. I'm buying 40% of this guy and 60% of my entire stock from this guy. Now, here comes a customer and he wants a green ball. Now, what I do with all the balls which I am receiving from those guys, well, I just put them in one very big box. And there are whites, yellow, green, another white, another green. So all the balls are together in one big box from all these guys. Now, what do I know about the contents of this box? Well, I know that 40% of this box comes from supplier X, and out of these 40%, 50% are white and 50% are green. Now, 60% of the entire box belongs to the second supplier, and out of these 60%, I know that 90% is yellow and 10% green. Now, if I just randomly pick the ball from this particular box, what's the probability of this ball to be the green one? This is a perfect example of this formula. Look at this formula. What do I know? I know this. The probability of getting the ball manufactured by supplier X is actually 40%, 0.4. I also know that if this is a tennis ball produced by the manufacturer X, then the probability of the event A that this ball is green is equal to 50%. I also know the probability of getting the ball from the second supplier. That's 60% I'm getting from it, right? So this is 0.6. And finally, I do know that the probability of getting a green tennis ball manufactured by the supplier Y is equal to 10%, 0.1. And that's what gives me the total probability of getting the green ball, which is what? 26, 0.26. So, if I just randomly pick up the ball, the probability of this tennis ball to be green is 0.26 or 26%. That's where this total probability actually is applied. So, notice that this is a pure conditional probability problem. I have not yet used the Bayes theorem in the beginning of this lecture when I'm basically reversing the usage. A under condition B and B under condition of A, and they are expressed one over another. For this particular problem, I didn't use it. But now let's consider that this problem is solved. But what I'm interested in the real case, I'm interested in the following. My customer wants actually a tennis ball which is manufactured by, well, let's say the first manufacturer. Now, if I'm picking up the white ball, then obviously this is manufactured by the first supplier, because white ball is only from this guy. If I pick the yellow, it's obviously from the second supplier, white, right? But what if I pick the green one? And this is my next problem, and that's where I'm going to use the Bayes theorem. So, what is the probability that this tennis ball is manufactured by the first supplier if I pick the green one? Because again, the probability of this, if I picked white, is 1, right? Because there are no more suppliers which are manufacturing the white. So if I pick the white ball, I know with the probability of 100% that it's manufactured by X. If I pick the yellow, the probability of this yellow to be manufactured by the first is equal to 0, right? Because all 100% goes to white. But if it's green, it needs some calculations. So what exactly are the calculations? So that's my next problem. Okay. Let's just reverse all these calculations. I know what basically I'm supposed to get is the probability of X under condition A, right? The probability that my tennis ball is manufactured by X if it's green. Okay? That's what I need to know. Now let's recall the Bayes theorem. Well, obviously I don't remember the formula, but I do remember that P of A over X is equal to P of A and X over P of X, right? And P of X over A is equal to P of, again, A and X divided by P of A. So this one is equal to PA and X, which is Px times P of A over X divided by P of A. Okay. So as you see, I just decided to derive the formula on the fly rather than remember it. Okay, I know that. Now, is that sufficient? Oh, well, let's think about it. P of X, I do know. That's 0.4. 40% is manufactured by the first guy. Conditional probability of getting green from X is 50%, right? So it's 0.5. And P of A, that's a total probability, which includes both manufacturers, this and this. And I have just calculated it. That's this formula. And there is a result, which is 0.26. So the whole thing is equal to what? 0.20 divided by 0.26. And I think I calculated it somewhere. Right, it's 0.77. So if I pulled the green tennis ball from the box randomly and it appears to be green, then the probability of this particular tennis ball to be manufactured by my X supplier is 0.77, which is 77%. And obviously the corresponding probability of this particular guy to be manufactured by the Y supplier should be the opposite, right? Let's do it. The probability of Y under condition of me picking the green ball is equal to P of Y times P of A under condition Y divided by P of A, which is equal to the probability of getting Y, it's 60%, which is 0.6. Conditional probability of the green tennis ball, if it's manufactured by Y, is 10%, 0.1. And this is still the same 0.26. This is the total probability of getting the green ball. And that's equal to 0.06 divided by 0.26, which is approximately 0.23, which is 23%. So under all these conditions, all these numbers, if I pick the green ball, my probability of having this tennis ball manufactured by the first guy is equal to 77%, and by the second supplier 23%. If I have picked any other tennis ball, then everything is obviously, if it's white, then it's 100% to this guy, and if it's yellow, it's 0% for this guy. So I'm talking about only the probability for the first one. All right? That's it. I suggest you maybe to read again. These all these calculations and formulas are in the notes for this lecture. And again, it's always good to register on the website on unizor.com. It's completely free, and that would enable you just to go through a complete course with enrollment and taking exams, etc. So that's what I definitely recommend you to do. All right, thank you very much, and good luck.